Good evening and welcome everybody to this very exciting event that we are about to witness. My name is Carlos Frank. I'm the chairman of the Royal Society Public Engagement Committee, and it is my great pleasure to introduce this evening's event. Before I do that, I have a couple of important announcements to make. The first one is please make sure that your mobile phones are set to silent. You don't need to switch them off in case you feel like sending tweets about what you're about to hear, but please set them to silent. Now, there are no planned fire drills tonight, so if you hear a bell, very loud bell ringing, please make your way to the fire exits, which are that one over there, and then at the back where you came in. Now, the event is being streamed live and recorded for the Society's archives. And so there is live subtitling and also British Sign Language interpretation. So those were the announcements. Tonight we're here, of course, to celebrate the 2019 Michael Faraday Prize, which is being awarded to his namesake, Sir Martyn Poliakoff. Now, the prize, of course, honors Michael Faraday, the great 19th century scientist who was and remains one of the most influential scientists of all time. Faraday discovered electromagnetism, and he also made pioneering discoveries in electrochemistry. But he was not just a brilliant scientist, he was also a brilliant science communicator. In 1833, he was appointed the first Fullerian Professor of Chemistry at the Royal Institution of Great Britain. And when he was there, he came up with the idea of the Christmas lectures, which survived to the present, and are in fact one of the highlights of the scientific calendar of the year in the media, on television. However, Faraday gave no fewer than 19 Christmas lectures, and they were attended by all the great and the good. And there's a story that after one of his wonderful lectures where he demonstrated electricity, the then Chancellor of the Exchequer, Sir William Gladstone, came up to him and said, well, all these sparks, all this electricity, this is all wonderful, but what use is it? And Faraday is reputed to have replied, I don't know, but there is every probability that you will soon be able to tax it. We say that to politicians very often. Now, the Faraday Prize is given annually to a scientist or engineer who, in addition to being an outstanding researcher, is also an outstanding communicator of science, as Martyn Poliakoff is. Now, he, as a winner of the Faraday Prize, he is in very good company. Previous winners include Harry Kroto, Martin Rees, Marcos Dusatoy, David Phillips, who's here, Jim Al-Khalili, David Attenborough, Brian Cox, Kathy Willis, and Danielle George, just to name a few. Now, Martin is a professor of chemistry at the University of Nottingham, and he is one of the foremost experts in the world on green chemistry and on supercritical fluids and on the application of chemistry to chemical engineering processes. You will hear, I think, about that very soon. Now, he's not only like Faraday, a brilliant scientist, he's also a brilliant science communicator. You'll be able to judge by yourselves in a minute, but he is also a YouTube star. Nearly 12 years ago, he teamed up with video maker Brady Haran to create chemistry videos for YouTube. Many of you, I'm sure, will have seen some of those. His channel has 1.3 million subscribers, and there are nearly 20 million views of his most popular videos. So if you haven't seen them, I really recommend them. So I'm delighted this evening to present the winner of the 2019 Michael Faraday Prize, Sir Martyn Poliakoff. Faraday's 1841 Christmas lecture was entitled The Rudiments of Chemistry. So it seems fitting that today's lecture has the title The Elements of Chemistry. Martin.
So thank you very much, Carlos, and welcome everybody here in the Cone Centre and online. The Royal Society is very innovative. It has been for 360 years, and I have a new sort of pointer. So if it doesn't work, you will have to forgive me. So let's get going. I'm Martin. The title of my lecture is obvious. I'm from Nottingham, home of Robin Hood, and currently the greenest city in the UK. And the aim of my lecture is to describe how chemists, like me, have quite strong relationships with particular elements. And I'm going to do this by giving you 4 examples how a relationship can start. That's by trying to answer a question, by being drawn into a relationship, by making a systematic search, and by complete chance. And I'm going to do this by giving you a brief tour of my office. So this is the entrance to my office. So ignore the bottles up here for the moment and just focus on this periodic table there. And this periodic table, which was devised for last year's International Year of the Periodic Table by the European Chemical Society under the leadership of my friend David Colt-Hamilton, and it shows the abundance of the different elements on the planet, but it also shows the number of elements in a normal mobile phone or smartphone. There are about 31. Now, I could have cheated and say, I love my phone, therefore I've got a third of the periodic table in my pocket. But my feeling is that most people who are obsessed with their phones are not obsessed with them because of the number of elements, any more than people love their partners because their partner's body contains 22 elements. So you can see a mobile phone is chemically much more complicated than a human being. But I'm going to give you much more specific examples. And my first example is by trying to answer a question, and it involves 2 elements, iron, Fe, and argon. Now, when many people go into my office, the first thing that they see is this box or these boxes, and they get a bit surprised by seeing these in a chemistry professor's office. But I teach chemistry, and I use dog toys as molecular models. And if you look, there is one here, a sort of yellow one, which I've got here. It's called an air dog squeaker. And it has the same shape as this molecule here, iron pentacarbonyl. You can see it's got iron in the middle and 5 groups, but it has the advantage compared to the molecule that it squeaks. And this really quite excites the students when I talk to them. I should say that chemists are rather coy in ever showing you chemicals, so I'm trying to show you a few. And this is iron pentacarbonyl, sorry. Iron pentacarbonyl, which is a sort of orange liquid. And so this molecule, FeCO5 compound, was part of my PhD with Jim Turner, who I'm delighted to say is in the audience here. And so Jim posed me quite an interesting question, which was, if one of these CO groups fell off the molecule, what shape would the bit that was left take? So would it be sort of tetrahedral shape, or this funny shape here, or a square one? And the question is how you can find out. But Seb, just come and give this to the audience so they can have a play with it. So now, the problem is that this molecule, when you take a bit off it, is going to be very reactive, so you can't just study it normally. And so Jim, when he'd been in America, had learned a new technique called matrix isolation, where you immobilize molecules in a solid at low temperature. And if they're cold, they don't have so much energy, so they don't move around. And perhaps it's better explained with this cake, which the picture hangs up in my office. And you can imagine that if a molecule which is of iron pentacarbonyl is embedded here, you shine light on it, and the carbon monoxide, which is shown here by the currents, fall off, and they're held rigidly in the solid, so they can't get out. And I should thank my sister Lucinda, who's here, who helped me make this cake more than 40 years ago. I'm not going to tell you how we did it. You can ask in the questions if you want to. But you obviously don't use a cake, but we use solid argon, because argon is very unreactive inert gas at 20 degrees absolute, the boiling point of liquid hydrogen. And in my office, sort of stuffed in a corner, is the hydrogen liquefier that I used in my PhD. It's upside down because it doesn't stand up the other way, but I still have a big attachment and it's just stuck in the corner. So I occasionally can reminisce to people about it. And this is what the apparatus looked like in 1970 when Jim proudly gave a lecture to the Undergraduate Chemical Society, and I wheeled the apparatus in to show them. Now, in those days, we didn't have cameras and take pictures all the time, so I don't have a picture of the matrix of iron carbonyl, but I do have a picture of chromium compound, and you can see it has this rather nice purple color. And this, though you may not think it, is at 20 degrees absolute. There's no scale, but this is about the size of a ring pull on a drinks can. And obviously, when the molecule is in the solid, you can't take it out and analyze it, so you have to look at the absorption of light. And in particular, we use the absorption of infrared light, which is absorbed by the vibrations of molecules, vibration of bonds. And this is my wonderful spectrum. I'm still proud of it, God knows how many years later. So this at the top is the spectrum we observed. You can see it has a sort of diagonal line of peaks getting smaller and smaller. Each thing pointing down shows the absorption of infrared light, and underneath are two spectra calculated using very primitive computer program for different shapes of molecules. And you can see this one down here is not very good. Instead of having the diagonal line, it just has two peaks that are big. But this one here looks really very like the original one. And so we could work out the shape of the molecule, and it had a bond angle of 145 degrees here and 120 degrees there. So I now show you the most expensive dog toy I have ever bought. So don't steal this one. And so you can imagine the molecule started when the CO came off. It started with these two straight, and they just relaxed a bit. So the answer to our question was that if you take off a CO group, it goes from that shape to that shape. And you might say, well, that's obvious because that's what you might expect. But nobody thought of it before we did those experiments. And like many things in science, it's obvious after you know the answer. And this shape actually had all sorts of implications about the way the electrons were arranged in this molecule. And my colleague Mike George has since done wonderful experiments which show that Jim Turner and I were right, and that this is the shape. So, Anna, come and give them this to look round. They'll probably still enjoy it, even if it doesn't squeak. So now I want to go on to the second thing, which is being drawn into a relationship. And this involves the element hydrogen, and I'm going via xenon and carbon dioxide. Now, of course, carbon dioxide is not an element. It's carbon and oxygen, but you're all grown up enough to understand that. And so we had a problem that when we were doing these really low temperature experiments, some of our compounds were much more stable, or appeared to be, than we expected. So we wanted to examine them in solution, but still using infrared light. So we needed solvents that were transparent to infrared light. And as I said, the infrared light is absorbed by the vibration of the bonds between atoms, and most liquids have molecules with lots of bonds, so they absorb a lot of infrared light. But argon, krypton, and xenon have only one atom in the molecule, so they can't vibrate, and they can't absorb infrared light. So Jim and I started working in liquefied noble gases. And on the bookshelf in my office, there is this report here from the SERC, the Science and Engineering Research Council, from 1985, with the picture of my then student Rita Masis on the front of it. And Rita is now a professor in the States. And on the other side is a picture which now hangs in my office of the cell in operation with liquid xenon in it. And not many people have seen liquid xenon, so you're really privileged. And you can see it looks a bit boring. It doesn't absorb light. It just looks like a colorless liquid, so it was great for studying dissolved molecules. And I still have the cell in my office, and we don't use it anymore. But what I want you to see is that it's got all these bolts sticking out of it because the windows needed to withstand quite a high pressure. And the reason why it needed to withstand high pressure is that argon, krypton, and xenon have a very short liquid range between their melting point and their boiling point, only about 4 degrees centigrade. But if you increase the pressure, the liquid range is extended, so eventually, at about 20 atmospheres, they all overlap. So you can go from nearly minus 200 degrees up to about just above minus 40 degrees, which was the maximum temperature that our cells could, and maximum pressure that our cells could withstand. Any higher and pipes started bursting, which was very expensive because xenon is an expensive gas. So some of our molecules were still stable, and we wanted to go to even higher temperatures. And so we needed higher pressures. But you cannot go on increasing the liquid range of something just by increasing the pressure. You can understand this with a diagram like this, which is called a phase diagram. So you have gas here and liquid, and as you heat, the boiling, there's pressure along here and temperature up here. As you heat, the boiling point goes up, but then suddenly it stops. And this is quite an exciting effect. I shall try and show you this on a video if the Royal Society computer works. So, So imagine you're heating a cell with a gas and a liquid, and it starts boiling, and material goes from the liquid phase into the gas phase. So the pressure here and the density goes up, and the liquid expands, so the interface disappears eventually. And you have a highly compressed gas. And then when you cool it down, you get this storm effect. And I think the first time I saw this, I fell in love. And I used to have the apparatus to demonstrate this in my office. There's now so much junk in the office, there isn't room. And I used to use this to demonstrate to prospective research students, and if they looked at it and went, wow, I knew they were suitable to work with me. If they looked bored, I suggested they should work with Professor X, Y, or Z down the corridor. And of course, I didn't discover this effect. And it was discovered by one of our fellows, Thomas Andrews, in 1869. He was at Queen's University, Belfast. And when the fluids are above the critical point, they're called supercritical fluids. But they're really just highly compressed gases, carbon dioxide, xenon, or even steam, which can be used as solvents for reactions. And this thing here, which is a photo that hangs in my office, is actually Thomas Andrews' original model of the phase behavior of carbon dioxide, which is still at Queen's University in Belfast. So I have it there hanging. So last year was the 150th anniversary of supercritical fluids. Unfortunately, it wasn't the international year. But I worked with my then student Steve Howdle, and we designed a cell which would withstand the high pressures so we could do reactions in supercritical fluids. And because we were using infrared spectroscopy, we went on using xenon. I'll tell you what happened to Steve in a minute. And one of the things we realized was that supercritical fluids would give real advantages in reactions with hydrogen. So usually, hydrogen is not very soluble in liquids, and you have to mix them really hard to get the hydrogen into the liquid. The supercritical fluid is a gas, so hydrogen's a gas, and they mix completely. So this slide was originally designed for primary school children because you can see blue and yellow mix and give green. So what this means in supercritical fluids, you can have really high concentrations of dissolved hydrogen. And Steve and I used this to make this rather strange compound, CP manganese dicarbonyl dihydrogen, which was the first dihydrogen compound of manganese. You can ask, why did we want to make this? Well, nobody had made such a compound before, and chemists are expected to make new compounds. And then, of course, we made this on a really tiny scale, and we wanted to make enough of the compound so we could see. So with our then student James Bannister, we designed a flow system so you could flow the gas over the starting material so it would dissolve, then use various spectrometers to make sure the reaction was going okay, and then precipitate out the product just by expanding the gas. And here is a very miserable amount of this compound. You could ask, why have I shown you such a dreadful photograph, such a miserable amount? The answer is this is the only new compound that I've ever made, or rather my research group has ever made, so I felt really proud of it. And then my research really quite changed with the invention of a new discipline called green chemistry. And green chemistry is quite a simple idea. It is devising cleaner, environmentally more acceptable ways of making chemicals and materials. And the aim of the green chemistry is to do something in the lab, and when it works, transfer it into industry. And one of the things that are used a lot in the chemical industry are solvents, which are often toxic, and carbon dioxide, for example, is relatively innocuous. You breathe it in and out, you drink it in beer. So because we're working in supercritical fluids, we were in a good position to start working this area. And then a really strange thing happened. An article was written about supercritical fluids, including our work, in the journal New Scientist in the summer of 1994, under the title, "Solvents Get the Big Squeeze." I was a bit disappointed by the article. Didn't make enough about our research. See, it had other people's research as well. And, but then, about 2 or 3 months later, quite late at night, I got a phone call at home from this gentleman here, Thomas Swan, who's now sadly died, who at that time was the owner of Thomas Swan & Co., which was the second largest private chemical company in the UK. And he phoned me up and said he wanted to collaborate making chemicals in supercritical fluids. This is like a dream for an academic, to be phoned by somebody who wants to work with you. And so we worked together on reaction called hydrogenation, adding hydrogen to organic compounds. And so the idea is that you have the substrate, which is the thing you want to react, and hydrogen, which is mixed with supercritical CO2 with a little mixer. It is passed through a reactor that contains catalyst, reactant turns to product, and here you release the pressure, the product goes that way, and the CO2 goes that way. And here is my former postdoc, Pete Licence, in the lab with here's the mixer, there's the reactor, and the product comes out at the end. So the reactor's quite small, and I brought a double-sized reactor in the hope that you might actually be able to see it. And it's just an empty tube. You can see if I take a Royal Society pencil, it just falls through it. And the tube contains the catalyst. This one does make quite a nice noise, but I won't pass it round because it's a bit boring. And so we did the experiments in the lab, and then we scaled it up to build a full-scale chemical plant of 1,000 tons a year. And you can see here is the reactor, and there's a worker here just to give you a scale. And on the wall of my, here, this is the first bottle of product. You can see here, it says batch 1. For those of you who are interested, this one here, the starting material, is called isoferrone, and the product has a really unromantic name. It's called TMCH, trimethylcyclohexanone. And I was given this first bottle of product, and I sat in my office admiring this bottle all morning. And then a student came and said it was needed in the lab. And I've never seen it since. But on the wall of my office, there is an invitation to the grand opening of the plant. It's been in the sunlight, so my name has nearly been completely faded by the sunlight. And unfortunately, I couldn't go to the grand opening because it was the same day as the admission ceremony where I was admitted to the Royal Society on the stage. So my postdoc, Pete Licence, went to the opening and demonstrated supercritical fluids to the then Science Minister, Lord Sainsbury. Pete Licence is now a senior professor at Nottingham and director of our carbon neutral lab. And I was so proud that my long-suffering wife was taken to see the plant. And this is my former student, Fiona Smale, who worked for the company and now works in Cambridge. And I should say that, that I'm quite sad that Janet has injured her foot, so she can't be here today. Perhaps she's watching now. Hello, Janet. And so Now, the plant itself was a huge technical success, but the price of energy went up and it wasn't economic to run anymore. So you can ask, what was really the point of the whole thing? And the first thing is that Thomas Swan, which in those days was quite a small chemical company in the UK, was listed in 2001 as among these so-called mothers of invention, as one of the top 20 most creative chemical companies in the world, most innovative. So it really was a very big boost for the company. And it made me interested in chemical engineering to the extent that I became a fellow of the IChemE, and 3 years ago I became a fellow of our sister academy, the Royal Academy of Engineering. And I and my two colleagues, Steve and Mike, exhibited at the Royal Society Summer Exhibition in 2002 about supercritical fluids. Both of these were my students. Steve now is the head of the School of Chemistry at Nottingham, and Mike is deputy head and leader of the research group that I work in, so they're now both my bosses. And so I'm very proud of them. So now we come on to the next story, which is making a systematic search for elements. And this has 4 elements: cobalt, copper, nitrogen, and bromine. And this is where the plastic bottles come in. My office is absolutely full of plastic bottles, which I collect. And this one here is my latest one that I got last month. And this came from the Great Hall of the People in Beijing. You can see I photographed it there before I drank the water. And the reason that I'm interested in these bottles is obvious if you look at the bottom of the bottle, and all of them have this recycling sign here saying PET, and the T is terephthalic or terephthalate, which is derived from terephthalic acid, which is this molecule here. And terephthalic acid is made in huge quantities across the world, and it's made from a starting material called paraxylene, and the reaction is carried out in this molecule here, which is acetic acid, or some of you who are younger may call it ethanoic acid, which is the principal component of vinegar. And it has a catalyst with manganese and cobalt, and this is done on a big scale. Nowadays, a 500,000 tons a year plant is considered quite small, but it's often energy intensive. You have to put in quite a lot of energy to get the reaction to go. And the main drawback is that the terephthalic acid is insoluble in the acetic acid. It precipitates in an impure form, and half this giant chemical factory is needed to purify it. So, in collaboration with ICI, the then company ICI, we came up with the idea that perhaps we could do the reaction in supercritical water. This is water at very high temperature, 374 degrees centigrade, 218 atmospheres. These are temperatures and pressures where you begin to think you have to work carefully in the lab. And the interesting thing is that many of you will know that water has hydrogen bonds between the molecules, and as you heat it up, these bonds begin to break. And so by about 300 degrees, water becomes much more like an organic solvent. Organic compounds will dissolve, but oxygen will also dissolve in supercritical water, just in the same way that hydrogen dissolves in supercritical CO2. So the question was, could we use this to make terephthalic acid? So the vision was that If we took the reaction with paraxylene, oxygen, making terephthalic acid and water, we would have no organic solvents and a so-called homogeneous reaction. That means everything would be dissolved right the way through the reaction until the end. So there are a number of minor technical problems. The first one is that you are mixing oxygen and an organic compound at high temperature and pressure, which is a recipe for things potentially going catastrophically wrong. And you need to mix with the catalyst, and then you get the products. So the key questions were, how do we mix the things safely, and which catalyst to use? So if you just look at the table in the middle of my office, which is a terrible mess, there is this object here, which is shown there, which is one of our reactors, and the student in question forgot to put in the thermocouple that controlled the heater, and the aluminium block melted somewhat above 600 degrees centigrade, and the liquid aluminium flowed down to the bottom. So I think this looks really beautiful, and it's quite a warning to people to be careful, so it sits on the table. But we solved these technical problems, and this is the first successful version of our reactor. The xylene goes in here, the products come out there, and this is my then student Eleni Vernadou, who's from Greece, and Eleni has now gone back to Greece and working successfully in chemical industry in Greece. And the question was, which catalyst should we use? Because the traditional catalyst that's used in acetic acid is known to be killed. It doesn't work as a catalyst in the presence of water. So rather unimaginatively, we went right through the periodic table, or most of it, and the elements in green turned out to be the ones that were best. This was a mixture of cobalt, copper, ammonium ion. I know ammonium is not an element, but it looked nice putting it there. And bromide. And if you use these four, you get very good reaction, efficient reaction in supercritical water. And you can see this here. When, oh God, what's happened here? Something's happened to your computer. I will have to start. Or are you going to start it, Paul, or shall I? There you are, nearly there. Keep going. More? It's not on the screen yet. Okay, one more. Two more. Okay, I can take control. I don't know what I did. So here, I must be more careful with this new machine. By the way, I meant to be the first speaker who's ever dared use this machine. So I feel quite proud even when things go wrong. And so you can see that when the terephthalic acid, when things are not quite right, it comes out looking like bran flakes. And then as you get things right, it comes out as a purer white color. And we got really quite good results at the end. This was an immensely long project. It lasted from 1995 to 2018, which is 23 years, nearly half my independent scientific career, involved a whole series of people in Nottingham, the ones in green, and in the company Invista Performance Technologies. ICI, well, the team worked for a company that changed its name 5 times during this project, and this is the final name. Now, the lab work at Nottingham and at Invista went very well, but then it was decided there wasn't a big enough commercial case to build the next size of pilot plant. So at this stage, the project finished and isn't being taken forward. But were all sorts of things that were successful, and I've just highlighted two. First of all, Duncan Housley, who's long-time employee of Invista, got a PhD part-time working with me in Nottingham while at the company. And my colleague in Nottingham Chemical Engineering, Ed Lester, spun out some of the technology into a company called Promethean Particles, which you may be able to read up here, is now describes itself as the world's largest continuous multi-material nanoparticle manufacturing plant. And it's in Nottingham using supercritical water. So I feel very proud that Ed has taken this forward. And you can read about it on their website. So now we come on to elements by complete chance. So in Carlos's introduction, he didn't mention that in 2011, I was elected Foreign Secretary and Vice President of this society. And if you don't know what the Foreign Secretary does, there is a mission statement in the 1663 Charter. And it says, to enjoy mutual intelligence and affairs with all manner of strangers and foreigners. So this is what I did for 5 years. And in effect, I was an ambassador for UK science, and importantly in this case, I did all sorts of odd jobs representing the Royal Society at different events. And in the end of 2012, beginning of 2013, the Royal Society had an exhibition called Romantic Chemistry. This is chemistry in the Romantic period, that's beginning of the 19th century. And the exhibition was sponsored by a company called CBMM, which is a large Brazilian mining company and one of the world's largest producers of the element niobium. So since I was a chemist and Foreign Secretary, I was asked to speak at the launch event and to give a talk on the chemistry of niobium. Now, there was only one problem. I knew nothing about the chemistry of niobium. But my father used to say that our family motto is, it is better to be lucky than efficient. And in this case, I was extremely lucky because I was corresponding with a Chinese student who wanted to do a PhD with me, whose email address was similar to niobium34@gmail. I should say, because of data protection, I have changed this email address slightly, so there's no point trying to email him. Anyway, I asked him why he was called niobium. He had this email address, and he said because he really loved niobium. And so he told me some basic facts about the chemistry. And because one must always acknowledge one's sources, I mentioned this when I gave the talk. And the talk was a great success. As a complete surprise, at the end of the talk, CBMM offered to pay for his PhD with me. And he then decided that he wanted to take a higher paid PhD in Italy, but CBM very generously said they would fund another Chinese student, whom we found, and the one we found was called Jing Jin. And the question, or the scientific problem we decided to focus on, is that niobium phosphate, which to a non-specialist chemist looks a bit boring, turns out when it's wet to be as strong an acid as sulfuric acid, but it's a solid. So the question was, could we use niobium phosphate as a greener acid catalyst? And together with Mike George and Jing Jin, we published 3 papers to show that this was, indeed, we could do quite interesting reactions. I won't go through the details, And here is niobium phosphate on the front cover of the journal Green Chemistry. And so the CBMM were very pleased. So Jing-Jin was a joint student with Mike and me, but Mike didn't want to go to the mine in Brazil, so I had the chance of going to the mine in Brazil. And here you can see I was really surprised. I expected the mine to be really dirty and so on, and instead it was green, even had a zoo. So you can see here is Jing-Jin and me. They wanted me to wear a hat for the photo, so I looked even funnier. And so now in my office, I have several souvenirs of niobium. I have a medal, which I didn't win, but I was just given the medal, which has a picture of Charles Hatchett, who was the romantic chemist that discovered the element niobium, and this is made out of niobium. And here, under the blackboard, or whiteboard rather, in my office, there is a sample of the ore from the mine. Niobium itself ores are colorless, but it has an iron oxide, so rust impurity, which is there. And over here, there are some bits of metal, which is so-called ferroniobium, which is a mixture of iron and niobium, and which is used for making cars or strengthening cars. And so at this point, I was going to do a demonstration, but I can't. Well, I was going to be given some paper by the Royal Society, who forgot to, so I will have to sacrifice a piece of paper. And so if you take a piece of paper, it's pretty strong when you pull it. But if it has a small flaw, like a tear, then if you pull it, it immediately comes apart. Don't worry, you can stick them together again. And but the steel that you use for your car, to build cars, is made out of so-called grains, or small crystallites that have boundaries between them, which are, the boundaries are a sort of source of weakness. If you add a little bit of niobium to the steel, it accumulates in the grain boundaries and stops the cracks spreading, making the steel much stronger. And at Arashad, where the mine was, they had this fantastic car body where it showed with the different colors the amount of niobium in the steel, because you don't need the whole car to be equally strong. You want it to collapse at the back if somebody hits you, so you're not injured so badly. But you want the roof to be really strong so it doesn't collapse if it turns upside down. And so I thought this was really nice. I never thought about how you made steel for cars. And by putting in 200 grams of niobium, you can save 100 kilos in the weight of an average car. And so that, if you think about the amount of petrol and emissions that is over the years, that's a huge amount. So now, this really brings me to the end. When I was looking at the booklet about the romantic chemistry, I discovered or remembered that I had, as Foreign Secretary, I'd had to write the introduction. And I've decided that this bit of the introduction here that's in yellow is quite a good summary of my lecture. So I'm going to read it to you. And so it says, long before today's mass media, that's the romantic chemists who discovered these elements, were almost stars, as witnessed, for example, by the popularity of Davies' lectures at the Royal Institution. It's sad that so many modern scientists are shy of performing to the general public. Communicating with the public is part of our scientific heritage, not an activity always to be delegated conveniently to professional communicators. But at the same time, modern scientists must be humble. They sometimes do not understand social media and can come across as pompous and boring. So I really want to thank my friend and collaborator, Brady Harron, who has taught me everything that I have learnt about how to present science in videos. And he's not shy of telling me when I'm pompous or boring. I should say that my son, who is sitting in the front row, gave me a birthday card in 1991 when I became a professor, which said, "Don't be pompous like other profs." And this still hangs in my office. And so I'm really grateful to Brady. I will just say that we're always looking for sponsors for our videos, so if any of you feel like sponsoring us, we will be delighted to accept your donations. And I also need to thank all of my mentors, my students. There are at least 3 of my former students here, my co-workers, colleagues, and collaborators. And I would particularly like to thank Mike George, who is now leading the research group, Steve Howdle, and of course my PhD supervisor, Jim Turner, without whose help and constant criticism, I would not be here today. But obviously, I would like to thank all the people who funded our research, especially the current research from the EPSRC. But I would also like to highlight our technicians, and particularly our current technicians, Rich Wilson, Rich Meehan, and Mark Geiler, who make the 2 Riches make much of the equipment that we use, and Mark Geiler keeps all of the our research labs running. And technicians are really important, whatever area or level of science we're working in whether you're at school or university or in the research industry, the technicians are vital, and it's much easier to recruit a new professor than a new good technician. And among the technicians, one person I would really like to thank is Neil Barnes, who has featured in most of our YouTube videos and does all the experiments. My hands shake too much to do experiments. And you can see that Neil has a lab that is as nearly as eccentric as my office. And those of you sitting near the front will see that I'm wearing a badge which says, "I love technicians." Thank you.
Thank you very much, Martin. It was neither pompous nor boring. There is a certain air of romanticism about the way in which you approach chemistry. Now, I'm sure there will be questions from the audience, so please, if you have any questions, put your hand up, and I'm sure Martin will be very happy to reply.
Namely, there's one here in the middle.
Oh, yes. Your eyesight is better than mine, Martin.
Sir Martyn. Sir Martyn, I saw one of your videos on YouTube where you had the world's smallest periodic table made. It was actually etched onto one of your hairs. This is quite a random question. Are you thinking of selling it on eBay?
No, it's in my office. I have to say, one of my colleagues has made a smaller periodic table on silicon, but I want to get back and have another even smaller one on my hair. There was quite a touching story. One of my colleagues in physics had a friend who was dying of cancer, and he was raising money for the treatment. So I donated some of my plain hairs, and they were sold on eBay at about £30 a time. And raised quite a lot of money.
Actually, Martin, I have a question. With your So with your typical modesty, you showed twice some machine, and you said you put in all these sorts of magical chemistry on one end, and product comes out of the other end.
Yeah.
But you didn't tell us what the product was. So I'm dying to know what these products are. Have we come across them in our everyday life?
Well, I mean that there is terephthalic acid, which is used to make plastic bottles. You could argue that perhaps you rather hadn't seen plastic bottles. And the other ones have been used, this molecule that we made, TMCH, you won't have seen, but is used as a solvent in fragrances, and also I think it may also be used in varnishes for nails, which you wouldn't necessarily have come across. The thing is that one of the points about green chemistry is most people don't realize that they're using chemicals. And if you show them some shampoo and say this shampoo has been made with chemicals that were made in a green way, people will tend to say, why didn't you tell me there were chemicals in this shampoo? I would buy a different one. And so I think that it is really important for us to make the chemicals that everyone needs. And the Royal Society produced a very good report in 2012 called People and the Planet, which pointed out that most of us consume too much, but 1.3 billion people are profoundly poor and don't consume enough. And so those poor people need to have more chemicals than we can make. So one of the things that is that we have to try and make more chemicals from the same amount of starting material. And because I come from Nottingham, I have formulated what I call the Robin Hood question, which is how can we give to the poor without robbing the rich, so that everybody can have the chemicals we need.
Are there any more questions? Yes, the gentleman here with the blue shirt.
Thank you, Sir Martyn.
There's a microphone coming because it's all being recorded for posterity.
Thank you, Sir Martyn. A frivolous question, perhaps, but is there any item from your long and distinguished career which you have not got in your office?
Yeah, well, I don't have many of the chemicals because, for obvious reasons, but I do have a lot of stuff which my colleagues always want me to throw out, and my secretary left in despair, so now no longer do I have a secretary. But I do have a lot of things, and very often things that haven't been used for a long time suddenly become very useful. I have a beehive shelf, if you know what that is, which was used in prehistoric times in chemistry labs, which suddenly one of my students needed to use. There's a woman here.
Is there another question here? The lady there.
Wait.
Wait a second for the microphone. There it is.
What are you or your group currently working on?
We're working on photochemistry, chemical reactions promoting by light. And we have a big project, for example, funded by the Bill and Melinda Gates Foundation for making artemisinin, which is one of the anti-malarial drugs. And we're trying to find a more efficient way of making them. And in 1912, that's more than 100 years ago, an Italian chemist called Cimician had a vision. He published a paper that we should try and make as many chemicals as possible with sunlight. Said, where you can grow food, you should grow food. Where you can't, like in the desert, you should make chemicals. And what we're trying to work on is new reactors which will make photochemistry more accessible to industry and to chemists as well.
Very good.
There's
I
one
think
right
there's one
at the
more
back.
question there at the back.
Hi. I just wanted to ask, what's been the most enjoyable part of your career?
Well, I think the answer is that research scientists are a bit like journalists. If you ask a journalist which is their most exciting story, they say the one that we're working on at the moment. So I would say the present is the most exciting time of my career, and I hope it will continue and get more exciting. But I have really enjoyed my entire career, thanks to the people who've worked with me and those like Jim Turner who have guided me. And I think it is really important when you're doing science that you should enjoy what you're doing, because in that way you will be really creative and you'll succeed.
I think we should close the evening, but Martin told us that as Foreign Secretary of the Royal Society, he was expected to engage in all manners of, in affairs with all manners of strangers and foreigners, but it is clear that Martin's, in his distinguished career, spanning now many years, the true affair he has had has been with these wonderful elements that the cosmos has put for us here on Earth. And your lecture's been absolutely wonderful, Martin, and I'd like to thank you for this lecture. And now I have the great pleasure of giving you both the Faraday Prize, and which I think is in here. It's a medal. It says the Royal Mint, so it must be a medal in it, and as well as a scroll that is the testimony to this prize that we at Royal Society has given you today. Congratulations, Martin.
Thank you.
Thank you all very much for coming, not just those of you who are here physically present, but also those of you who have been watching this wonderful lecture on the internet. And that's the end of tonight.
Thank you.